So I had mentioned earlier that if you get division by zero, then you have to deal with quotients a little bit differently. The question of what happens if you get something like 10 over zero, uh, we're going to deal with in another chapter. That's a different question. But what happens if you just substitute both the top and the bottom and you get zero? Now you might be tempted to say, well, the limit is undefined because you can't divide any number by zero. But actually, that's not true, and hopefully I can show you why with this diagram, but it's an important thing to remember that 0 over 0 is what we call an indeterminate form, which just really means that you need more work to evaluate it. It doesn't mean that it looks like I'm saying more work, more worth, or something like that, more work. Means you need more work to evaluate the limit. It's there are a couple of different techniques for it, but we're going to learn a very standard one here. So let's start by asking the question: what is the limit as x approaches zero of x squared over x? Now, let me just bring it over here for a minute because some of you are going to remember from algebra class. You're going to say, "Wait, I know this. My algebra teacher told me that x squared over x is just equal to x, right? So is that true?" The answer is no. It's actually not true. It's true for every number that isn't zero, but you can't divide by zero. So the answer is really that this is only true for values of x that are not equal to zero. The value if the value is zero, it's not true. If the value is not zero, then that statement is perfectly true. But remember, we're evaluating the limit as x approaches zero. So let me show you what the actual way of dealing with this is. If you look at this function here, the one in purple, this is the function y equals x. It's just a line with a slope of 1. It's a perfectly diagonal line that goes through the origin. Now look at the right. We have the function x squared over x. You'd think from what you may have learned in an early algebra class that these are the same function, but actually, if you look carefully, there's a hole in the middle of the green function because the function is undefined at zero. So I actually have to put this open dot on the origin to indicate the function is undefined there. It's for this reason that we say that the two functions are not equal, because we actually write that f of x equals g of x only if 1, they have the same values, and 2, they have, I know I'm really not writing very neatly here, they have the same domain. So the issue is that although these functions, the purple and green functions, have the same values every place where they're defined, their domains are different because the domain of the green function excludes x equals 0, while the domain of the purple function does not. But now let's go back to the ant. Suppose the ant is crawling on the purple function. Where does the ant conclude as we approach the function, the point x equals 0, where does the ant conclude its y value is going to be? The answer is it looks like this function is heading toward a y value of 0, and that's in fact true. So we say that the limit as x approaches 0 of x is equal to 0. On the other hand, the ant crawling on the green function is not actually, the function itself doesn't have a y value of 0 at x equals 0, but it's clear that that's where the ant would conclude that it's going to end up as it approaches 0. And for limits, that's the one thing that we actually care about, is not where you actually end up at 0, but where it looks like you're going as you approach 0. So the point is, these two functions have the same limit at x equals 0, even though they're defined differently at 0. So what we can do by this sort of division operation, let's get back now to what you learned in algebra class, what you can do is you can replace this function, you can replace this function with this one. And because they have the same limits, you can evaluate the limit of this function by evaluating the limit of this function. Now, why do we care? Let me show you. Because here, if I say that this is now equal to the limit as x approaches 0 of x, what do we have? We have a polynomial. So even though the quotient rule does not let us evaluate this quotient, the limit of this quotient directly because we get division by 0, what we can do is evaluate what we can do is evaluate the polynomial x. We can do the polynomial x at 0 directly and simply write that it's 0 because we know we can evaluate that polynomial by substitution. So what's the big picture here? The big picture is that sometimes you may be able to divide out a factor and solve the problem that exists in the quotient rule. If you're getting division by 0, if substitution gives you a 0 over 0 form, you can divide and you may be able to then evaluate by substitution. Let's do an example that's possibly a little bit more illuminating. So I have here the limit as x approaches 2 of x squared minus 5x plus 6. So first of all, let's verify that this is in fact a 0 over 0 form. Let's try substitution. In other words, let's replace 2 into both of these polynomials. We get 2 squared minus 5 times 2 plus 6 over 3 times 2 minus 6. That gives us 4 minus 10 plus 6 over 6 minus 6, which equals 0 over 0. So we do in fact have a 0 over 0 form. We can't just say the limit doesn't exist. In fact, I see this all the time on tests. It is wrong to say the limit does not exist. That's not true here. I mean, there are certainly 0 over 0 limits where it doesn't exist, but that's something you'd have to demonstrate in a different way. So we have to do more work in order to figure out what this limit is. So what we can do is we can factor these expressions, and we might be able to divide something out. So let's do that. This is going to equal the limit as x approaches 2 of, we're going to factor the expression on top. Hopefully you remember how to factor a quadratic. That's going to be x minus 2, x minus 3. And then on the bottom, I'm going to bring out a factor of 3, so that's going to be 3 x minus 2. So now we actually do have a factor. The same rule applies. In other words, we can say, just with reference to the previous example on the previous page, x minus 2, x minus 3 over 3x minus 2 is equal to x minus 3 over 3 as long as x is not equal to 2. In other words, x equals 2 is in the domain of this expression, of the function that's equal to that expression, but it's not in the domain of this function. So they are different functions, but they're equal to each other as long as x is not equal to 2. So we can cancel now and rewrite this as the limit as x approaches 2 of x minus 3 over 3, and that comes out, now we can do that by substitution. That's 2 minus 3 over 3, which is negative 1/3. Do another example along those lines. It's a little bit more complicated. So let's look at this function. We have square root of x plus 7 minus 4 over x minus 9. Surprisingly, this also comes out to a 0 over 0 limit. I'll just verify that by replacing the x with a 9. This becomes 9 plus 7 minus 4 over 9 minus 9. That gives us square root of 16 minus 4 over 0, which is 0 over 0, because the square root of 16 is, of course, 4. So so we can't do this we can't just do this by substitution. We can't just conclude the limit doesn't exist. What we can do is instead is try to divide something out. Now it's a little hard to see how to do that. When you see this type of expression where you've got one radical and one non-radical, what you often want to do is multiply by the conjugate. So I'm going to say that this is equal to the limit as x approaches 9 of the square root of x plus 7 minus 4 over x minus 9. And I said I wanted to multiply by the conjugate. Notice, by the way, how terms like that, like, go and multiply by the conjugate, like that just rolls off my tongue like that. When we say that you really need algebra skills to do this course, that's what I mean. Is like, you can't have to like pause and go look up what a conjugate is. You just have to know what it is. So the conjugate in general of a plus b is equal, the conjugate of that is equal to a minus b, whatever a and b are. So here, what we have is we have the square root of 7 minus 4. So, and oh, by the way, this works in the other direction too. We can say the conjugate of a minus b is equal to a plus b. So here we have square root of x squared minus plus 7 minus 4. So we multiply by the square root of x plus 7 plus 4 over square root of x plus 7 plus 4. I can't just multiply by the conjugate itself because I'd be changing the value of the expression. The point is, this expression, since it's just a thing over itself, is equal to 1, so I can multiply by that without changing the value of the expression. So this is now the limit as x approaches 9 of one nice thing about, let me just back up, I know I just stopped in mid-sentence. One nice thing about conjugates is that a plus b times a minus b equals a squared minus b squared. So let's take the square root of x squared plus 7. In other words, in that expression, it's like this is a and this is b. So square root of x plus 7 squared is just going to be x plus 7, and and 4 squared is 16, so that's going to be 16. And now we have x minus 9 times the square root of x plus 7 plus 4. There was nothing we could really do with that one on the bottom. We just have to multiply it in. Let's simplify a bit. This gives us the limit as x approaches 9 of x plus 7 minus 16 is going to be x minus 9. And then we have over x minus 9 times the square root of x plus 7 plus 4. So look at that. Looks like we actually, somehow, magically, we ended up with a factor of x minus 9. Turns out that in problems that look like this trick works. Oh, and I should say, it doesn't matter whether the square root part is on the top or the bottom. The trick works equally well, regardless of where the square root part is. So we can cross this out, cancel, and this becomes limit as x approaches 9 of the square root of x plus 7 plus 4. That equals 1 over the square root of 16 plus 4, which is 1 over 8. And that's the limit. Let's do one more of these. It's kind of similar, but it looks a little bit different. Let's evaluate the limit as x approaches 1 of x minus 1 over 1 over x minus 1. I realize it's kind of a compound fraction, but it's perfectly legitimate expression. So first of all, substitution clearly gives us 0 over 0. We have 1 minus 1 over 1 minus 1. That gives us 0 over 0. So we know that we're going to have to factor something out. Really just a little algebraic manipulation will give you something that you can factor out here. So let's see, this is going to be x minus 1 over, let's try to simplify that expression on the bottom. Let's multiply this 1 by x over x. So that's going to be 1 over x minus x over x. So that gives us the limit as x approaches 1 of x minus 1 over, and combine that compound fraction, so that's going to be 1 minus x over x on the bottom. This becomes the limit as x approaches 1 of x minus 1 times x over 1 minus x. So that I can do that. If I divide by a fraction, it's the same thing as multiplying by its reciprocal. So this becomes now the limit as x approaches 1 of, this is going to be x, I'm focusing that x comes from here, and it's going to be times x minus 1 over 1 minus x is the same thing as x minus 1 times negative 1, right? So now I have something that I can cancel out. There we go. So that's going to be the limit as x approaches 1 of x times negative 1. We can do that by substitution. That's just a polynomial. So that's going to be 1 times negative 1 equals negative 1, and that's that limit.